Good evening, everyone. Welcome back to the session, the learning space and our winter school. Remember, we started off yesterday. If you were with us in the science session, we kicked off organic chemistry. And then we still have to finish off the rest of organic chemistry. And then we've got Doppler effect, we've got electrostatics, we've got electric circuits all coming up. So, as you guys requested yesterday, I am going to continue and finish off organic chemistry. And then what we'll do is we'll just push all the other sessions to the next session. So meaning tomorrow we'll do electrostatics as well as Doppler effect. And then in the next session, we will then go through electric circuits. Fantastic, guys. So those of you who weren't with us yesterday, we made sure to cover the beginning of organic chemistry. As mentioned, organic chemistry does have three sections to it. So we've got nomenclature or naming. That's where you sort of do the IUPAC naming and drawing, all your structures, condensed structures, etc. Then we also have the second session and the third, which we're going to try and make sure we cover today, being your physical properties, boiling points, melting points, etc., as well as your chemical properties, your organic reactions. So we'll be covering those: addition, elimination, substitution, etc. So, apologies, my lights are falling in this place. So please just make sure, guys, that everyone who needs to be here is here. We had a lot of high attendance yesterday, so I'm pretty sure some of the guys are still coming. So if you do have a friend that you know you were with yesterday that needs to join the session, please send them a message right now. Tell them we're starting, we've got a lot to cover, and they better join the session. But a warm welcome. If you were with us yesterday, give me fire emoji, dancing emoji, anything in the chat, just so I can see that you guys are here from yesterday. If you are brand new to our session today, very warm welcome. Quick house rules for the day. One key thing is I want lots and lots and lots of interaction, right? So you'll see at various points in today's session, I'll ask you guys to engage or interact with me. How you can do that, you can use multiple features. So Zoom has reactions. So you can see right now there's lots of reactions coming up on screen. Thank you for showing us all the love. So you can give us reactions. The other way you can react is you can go post stuff in the chat. So Chantal, Zachary, Karabo, and Gabelo also posting in the chat. Welcome back to everyone from who was here with us yesterday. And then the third way you can engage with us is by using the Q&A feature. So because this is a Zoom webinar, we use webinars because they allow us to take a lot more people. A normal Zoom meeting limits us to 100 people. A webinar, we can take up to 1,000, and we want to be able to share the love as much as we can. So we then encourage you guys to use all of those three features. I need to also welcome our TikTok family. I know we probably are live on TikTok. I'll put my phone up just now just to make sure I can see all of your guys' comments. Again, TikTok, you only have one way to interact, which is the chat, but please make sure to utilize the chat. So I'll ask you to give me emojis, throw your emojis in there. If you're on TikTok right now, let's quickly see. Give me a fire emoji, a heart emoji, dancing emoji, whichever one sort of represents how you're feeling right now. And then as we go through the session, I'll ask you guys questions at various times. What I want you guys to do is to send me your answers. So sometimes I'll ask you, hey, there's a multiple choice. Simply post A, B, C, or D. Or I'll say, what is the value of this particular point, in this particular question, and then post that value. The reason why I always talk about that is because I want you guys to embark on what we refer to as active learning, right? This is an online lesson, yes, but it doesn't have to be less effective than an in-person lesson. At the learning space, we pride ourselves with presenting very engaging online lessons. So one of the better parts about engaging in the lesson, it means number one, you are taking part in the learning process. You learn nothing by sitting there and pretending you knew what was going on the whole time. You learn nothing by getting everything right. You learn a lot by getting things wrong. So even if you're scared your answer might be wrong, put it in the chat. Because the best part about getting an answer wrong during the lesson is that I'll get to see where your misconceptions are and I'll get to correct your misconceptions. And that's invaluable. When you're watching a video or a recording of the lesson after the fact, I can't help fix misconceptions. But if you post your answers, even if they're wrong and you're scared they're wrong, guys, being wrong is the best thing. It's literally how you grow, it's how you learn. So don't be scared of being wrong. It's very, very important, right? Shelly's asking, where do we find the previous live lesson? So what I said is that give us 48 hours to post the lessons on our YouTube. We will post links to all of our social media pages where you can find the recordings previously. And then as soon as I'm done with today's session, the notes and everything I take, I just wanted to finish organic chemistry before I posted my organic chemistry notes. So I am still going to post those in our WhatsApp community. Awesome. So without wasting time, guys, I want to jump straight into today's lesson. Quickly, before we get going, those who were here yesterday, how are you feeling now about organic chemistry? A lot of you guys are feeling nervous, very, unsure. You weren't feeling so awesome. How are you guys feeling now about organic chemistry? Quickly post that in the chat. Okay, Zach's feeling great. Mulukad is asking when are the live lessons going to end? I think next week, Tuesday, the winter camp is going to end. We extended it by 1 day just because I needed another day to cover organic chemistry. We were meant to run from Tuesday up until next week, Monday, but we've extended by another day just so we can cover more physics. Awesome. Zach's feeling great. Larato's feeling a bit more confident. Senzelo's feeling great. Karabo's feeling confident. Awesome, guys. Akum's feeling positive. Rakamala's feeling great. Debo's feeling great. More confident than I was. Very confident. More confident. Fantastic, guys. I'm loving that people are feeling better. That's what we're here to do at the learning space. Make you guys way more confident at this. And a lot of times, what you guys will see is confidence is everything, right? If I can have a word of the day, a lot of the times people think that their knowledge isn't where it needs to be, and it really isn't your knowledge. Your knowledge is there. You guys know what you need to do. The challenge becomes when you don't have the confidence to deliver what you need to deliver, you tend to remember less and you tend to be scared to take some risks, right? So you often try and maybe be modest with your answers. But if you just have the confidence in yourself to say, listen, actually, I have been studying, I have been doing this thing really well. Let me just give it my best. You find that you actually do get better marks. So one of the big pillars of the learning space is that we try and really help learners find their confidence in the subject. Because a confident learner is a learner who does really well. If you look at all the learners in your school who are getting level sevens and sixes and whatever, they're often not going to be super shy when it comes to their content. They're confident in their content delivery, in what they know. So make sure you're confident, guys, and that's the thing that'll help you get all your marks through. Awesome. So I'm going to jump straight through into today's content. And let me just share my screen quickly. So I'm going to start by sharing a quick little video. I want to honor this guy, man. I wish I knew what this guy's name was. So it's an educator who posted a really epic video of one of the classes he was running. I just quickly want to find, yes, this part of my screen, right? Before I go too far, TikTok family, welcome. Please, if you are joining us for the first time and you've never heard of the learning space before, click that follow button. Make sure you share the live and let people that are going to be with us join the session further, right? You'll see with the guys on Zoom, everyone is feeling a lot better about the subject, and we're going to keep on going. And hopefully, by the end of today's session, organic chemistry is going to be as simple as solving for X for you guys. That's my aim for today, right? Okay, I'm going to start you guys off with this epic video that I saw on TikTok, and I absolutely love this video because I really love when you get very passionate and creative educators. And this will be the kickoff for my lesson today. So let me quickly get my screen share going, and I just need to stop my video to save you guys some data. Okay, I hope it plays well. I'll play it twice. La letra. The stronger the higher the lower. The weaker the lower the higher. Playing the video again. La letra. The stronger the higher the lower. The weaker the lower the higher. So someone in yesterday's lesson was asking us for a method for memorization, and this is one of the best methods for memorization that I've seen so far, right? And it's how to remember the key things when dealing with the physical properties of organic chemistry. So I'm going to give you guys a quick rundown, a quick recap of all of that, and then I'll actually explain Ibomeva at the end of my presentation so that you guys really understand it. And then if anyone's brave, I'm going to ask you to unmute and sing the song for us, right? Let me quickly jump through some questions before I jump into my content. Okay, cool. How to enter the WhatsApp group? The link's been posted there. First time. Hope I enjoy the session. Yeah, Londile, you definitely will. Trust me, right? Lorato's already said that. Okay, I know this video is helpful during June exams. Yeah, it's epic. It's epic. It's epic. And then someone says, "Can you send the WhatsApp link?" The last time, I think it was sent in the chat. We'll copy it and send it again through. So let me quickly just share my presentation for the day, and then we can get started. Okay. Um, Let me just do this. Cool. Taffy or someone on the team just confirmed that you can see my screen. It should say welcome to the learning space. I just because I can't see my Zoom chats and reactions and that, but it's just for the presentation part. Okay, thanks, Shelly. Okay, awesome, guys. So let's quickly do a very fast recap on this, and then we can jump into some questions. Physical properties aren't as hectic, and then we're going to jump into I want to spend more time on organic reactions today, more than the physical properties, right? So dealing with the physical properties, I want to start off with a couple of definitions, right? So the definitions I want to go through, so we're going to look at boiling point, right? Melting point, as well as vapor pressure, just so that you guys understand what those things are. So again, so the boiling point is the temperature at which a liquid's vapor pressure equals the surrounding atmospheric pressure, right? We'll go through vapor pressure again, and you can quickly see what that is. But basically, you guys know it as the temperature at which something will change from a liquid to a solid, but that's exactly the same thing. It's when the vapor pressure equals atmospheric pressure. And why boiling point is really around pressure. There's a very fun thing that my physics teacher taught me when I was in high school. And they were talking about how when people went, I want to call it hiking, but it's not hiking. Climbing Mount Everest and Kilimanjaro is not hiking. Hiking is like 5 kilometers at Henops or 10 kilometers at Henops. Mount Everest is something different. Kilimanjaro is something different. But the higher they went, right, the pressure, the atmospheric or the air pressure at that point keeps getting lower and lower and lower. And when it gets lower, you find that the temperature that water boils at also gets lower and lower. So you find you could be up there and water will start boiling at 50 degrees Celsius or 70 degrees Celsius, which oftentimes isn't hot enough to actually cook certain foods. So you find people weren't able to like boil potatoes, for example, because at that point, the boiling point, which is not just temperature related, but also pressure related, wasn't enough to cook. And we actually underestimate little things like how atmospheric pressure can actually affect things like cooking. So boiling point is the temperature at which a liquid's vapor pressure equals the surrounding atmospheric pressure. So basically the temperature at which water will boil at a specific pressure. Very, very important. Then looking at our melting point, a little bit more simple, and melting point is simply the temperature at which a solid substance transitions into a liquid state, right? And finally, vapor pressure, it's the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases. So condensed phases simply meaning liquid or solid, right? Remember how when something is condensed, it's sort of the particles are more closely packed together. That's your liquid and solid phase. So at a given temperature in a closed system. So essentially, it's a measure of how easily a substance transitions into a gaseous state. So the higher the vapor pressure, right, that indicates that there's a greater tendency of something to evaporate. So the higher something's vapor pressure is, it evaporates way more easily, right? So that's generally how it works. Now, before I go into Ibomeva, I want us to kind of look at our intermolecular forces because these are the things that we really have to unpack. If you guys were there with us yesterday, you remember I was taking you guys through all the homologous series and the predominant intermolecular force for each homologous series, right? And the different intermolecular forces sit as this. And I want us to kind of go through the relative strengths because simply knowing what it is doesn't help if you don't understand the relative strength of the intermolecular forces. So the three I'm going to just focus on today are going to be your induced dipole, induced dipole. We refer to those as London dispersion forces, your London forces. Then you've got dipole, dipole, and then you've got hydrogen bonding. Now, how do we identify which molecules have that? I'm going to try keep it very simple for you guys. So usually your London forces, your induced dipole, that ID, those exist between molecules that are non-polar. So in that case there, think pure hydrocarbons, right? Things with just carbon and hydrogen, your alkanes, your alkenes. Nothing with an oxygen, nothing with a hydroxyl group, none of those things. So alkanes, alkenes, that's what you're dealing with in this particular case there, right? There are special cases, and I will touch on the special cases just now. But essentially, alkanes, alkenes, your pure hydrocarbons, London forces. That's where they sit. Then you go to dipole, dipole. So dipole, dipole, you're looking at polar molecules. So where you get polarity in molecules in organic chemistry is anything that's got an oxygen in it, right? Because oxygen then has a much higher electronegativity than carbon and hydrogen. And that gives you the polarity of the molecule where oxygen becomes slightly negative and the carbon hydrogen becomes slightly positive. So dipole, dipole, anything with an oxygen in it. Ketones, your aldehydes, your esters, your carboxylic acids, those will have dipole, dipole forces. Then you've got hydrogen bonding. Please note, hydrogen bonding is dipole dipole, just a special case of dipole dipole, right? So hydrogen bonding is a dipole dipole where you have an oxygen bonded to hydrogen, or hydrogen bonded to nitrogen, or hydrogen bonded to fluorine. In the case of organic molecules, the one we care about is the OH bond. So wherever you see OH, your hydroxyl group, your OH bonded there, just know that that point of the molecule will have a very strong intermolecular force ability at that point. So London forces are your weakest ones. So those are your pure hydrocarbons, alkanes, alkenes. Dipole, dipole, it's a notch above. So you're looking there, aldehydes, ketones, esters, and then hydrogen bonding is the strongest one, right? There you're looking at your alcohols, you're looking at your carboxylic acids, right? I mentioned carboxylic acids for dipole, dipole as well, because carboxylic acids will have the double bonded O on one side, and that can do dipole dipole bonding, and then they've got the OH on the other side, and that can do hydrogen bonding. So just keep that in mind, right? Let me quickly just pause for the chat. Someone says here, are we not supposed to be doing electrostatics and Doppler? No, Lutando, yes, we were. We just shifted the schedule slightly because with organic molecules yesterday, there was a lot of interaction, and we got through the end of nomenclature, and I wanted to continue and finish the section off. So we are going to cover all of the topics we said we're going to cover. We're just shifting everything out by a day, essentially. Hope that helps. Um, Okay, perfect. Then Kamano says, when do we know when carboxylic acids is dipole dipole? So carboxylic acids will have a part of it that's dipole that can do dipole dipole as well as hydrogen bonding. So the key thing that I want you to remember is pure hydrocarbons, London forces, alkanes, alkenes, right? Dipole, dipole, anything with an oxygen, that it'll have a dipole, dipole point where it can interact, right? And then if you get an OH in your molecule, hydrogen bonding, right? That's very important. You'll see it now when we do the application of this particular question, right? And then we'll go through it. All right. Karabo says you're moving too fast. Okay, Karabo, I definitely will slow down. If there's anything that you are unsure about, Karabo, please ask, and then I will quickly repeat that for you. So let me do one last repeat of the entire thing. All right. So again, induced dipole. We refer to this normally as our London forces. So that is for non-polar molecules. So non-polar molecules there, if that doesn't make sense to you, if I say polar, non-polar, just wait for our third term grade 11 classes. We'll probably do one there of chemical bonding intermolecular forces. But for now, I'll give you the high level version. London forces, pure hydrocarbons, alkanes, alkenes. Dipole, dipole, anything with an oxygen in it, right? Ketones, aldehydes. Mainly carboxylic acids can do it as well, but just think ketones, aldehydes. Hydrogen bonding, anything with an OH. Think your alcohols, think your carboxylic acids. And then dipole, dipole is also esters because it's got the double bonded O in there as well. And the O that's sitting there in the middle. That's basically how we go through it. Okay, cool. And then hello alkanes. So again, hello alkanes, you will then have, let's say if you have got fluorine, you got iodine or anything like that, those are going to be molecules that have a higher electronegativity than carbon. So you will end up with a dipole-dipole bond if it's short enough. But don't stress about that right now. So haloalkanes will be dipole-dipole. So like I said, the London forces is your pure hydrocarbons, like pure alkanes, pure alkenes, London forces. So there are special cases where a very long alcohol can have London forces, but I'll give you guys an example of what that looks like just now. Just keep in mind that certain molecules can use different types of bonding together, right? Okay. Then I want to quickly unpack the video we watched at the beginning, that Ibomeva. I like that so much. It's probably epic. So the whole Ibomeva, it's Ibomeva. That's The E is I, intermolecular forces. Bo is for boiling point. Me is for melting point. Va is for vapor pressure. E, bo, me, va. Intermolecular forces, boiling point, melting point, and vapor pressure. Then the guy goes, shh, la, la, which I think is pretty cool. But he's just helping you remember how to write everything in this case here. The third line is the opposite of the first line. So sh, la, lela is going to be stronger, higher, higher, lower. The third line, just the opposite of the second line. So instead of stronger, I go weaker. Instead of higher, I go lower. Instead of higher, I go lower. Instead of lower, I go higher. Let's unpack what that means. So what he's saying is that, right, in terms of intermolecular forces, the stronger the intermolecular force, the higher the boiling point. The stronger the intermolecular force, the higher the melting point. The stronger the intermolecular force, the lower the vapor pressure. And then the opposite is going to simply just be the weaker the intermolecular force, the lower the boiling point. The weaker the intermolecular force, the lower the melting point. The weaker the intermolecular force, the higher the vapor pressure. All right. And as we remembered now, strong intermolecular forces, what does that mean? It means my molecules are attracted to each other very strongly. It requires a lot of energy to take them apart. So when you think about a high boiling point means what? Remember, temperature is the average kinetic energy of the particles in a substance. So if I have to have a high boiling point, it means I need a lot of energy to break those intermolecular forces or to overcome the intermolecular forces. So when you've got strong intermolecular forces, you need a very high boiling point. So it requires lots of energy to evaporate something. And then a high melting point to convert me from solid to a liquid. That again, I'm overcoming intermolecular forces. I need a lot of energy. So that's going to be strong intermolecular forces. And that low vapor pressure means I've got a very low tendency of evaporating spontaneously, right? So if you've got strong intermolecular forces, you've got a low vapor pressure. There's a low likelihood or low tendency of just evaporating unnecessarily. All right. And then finally, the weaker, the lower, the higher. The weak intermolecular forces will give you a low boiling point. Weak intermolecular forces are very easy to overcome. So your boiling point is low. You don't need as much energy to overcome weak intermolecular forces. The melting point is also very low. I need less energy to overcome it. And then my vapor pressure is a lot higher. My tendency of evaporating is very high because my intermolecular forces aren't that strong. The molecules can come apart very easily, right? So this is a very cool way to remember your physical properties, your boiling points, melting points, vapor pressures. And I think literally in one screen, you can literally get the entirety of question three in your exam done. And it's literally that easy. Okay, hope that makes sense. Please, if that makes sense to you guys, drop me thumbs up in the chat, just so that I know you guys are with me. Okay, let me just pause for questions. Okay, someone says, please emphasize how we see if it's solid, liquid, or gas based on the degrees or based on the temperature. Okay, okay, so I will try and show that shortly as well. Normally, it's when they give you boiling point and melting point, and then just basically look at where the temperature sits. So if they said the boiling point was 10, right, and the melting point was 5, if my temperature is below melting point, it's solid. If it's above melting point, but below boiling point, it's liquid. If it's above my boiling point, it's gas. So what I would do for yourself there is draw a line. Let me maybe share my writing pad just so I can show that to you quickly. Let me stop sharing this and share my writing pad. Give me 2 seconds. Okay, so let me quickly do this somewhere down here on this page, right? So oftentimes, also, okay, so just confirm that I'm understanding your question correctly. Because you're asking me to emphasize how we see if it's liquid, solid, or gas based on the degrees. I'm assuming you're saying based on the temperature. So sometimes what they'll do is they'll say, here's, for example, H2O. We've got water, and they'll tell you the boiling point of water is 100 degrees Celsius, and then the melting point of water is 0 degrees Celsius, right? So what you need to do is kind of draw this for yourself. Just say, okay, cool. At some point, there's a line and there's a line. That line is your melting point. That line is your boiling point. Above the boiling point, we're dealing with a gas. Between melting and boiling, we're dealing with a liquid. Below melting point, we're dealing with a solid. And you know that, let's say this is 0 degrees, that's 100 degrees, then all you need to do is find the temperature that they give you. If they said that my H2O is 78 degrees, so I know 78 is going to be in this place, that's a liquid, right? If they said my H2O is 110 degrees, 110 degrees is here, that means it's a gas. If my H2O is negative 10 degrees, negative 10 is going to be here, that's going to be a solid. Quick, so just tell me if I did manage to get that right on your side. Okay, and then Oluchi is asking, is it always like that? Oluchi, I'm not sure exactly what you're referring to, but please just if you can elaborate. And then how can we see the chain length of the branches? Lue, I'll definitely explain that as we go through the question. You'll see how the chain length affects everything there. Shelly says, please repeat Ibomeva. Didn't understand you properly. No worries, I will do just that for you, right? So with our Ibomeva, let me quickly share that screen one more time. Okay, give me 2 seconds. Okay, so we should have this up again, right? So again, what we're dealing with here, E, bo, me, va. So I, the E is intermolecular force. The BO, the bo, is boiling point. The me is melting point. I wrote melting point. Apologies for my typing error there. And the va is vapor pressure, right? So the song goes E, bo, me, va, sh, la, lela. So the sh, la, lela is just to help you remember what order it comes in. So what that means is that the stronger, the higher, the lower. What that means is the stronger my intermolecular force, the higher the boiling point. The higher the melting point, the lower the vapor pressure. And then the last line is simply the opposite of the second line. Instead of strong, we've got weak. Instead of high, we've got low. Instead of high, we've got low. Instead of low, we've got high. The weaker my intermolecular force, the lower my boiling point, the lower my melting point, and the higher my vapor pressure. The reason being, strong intermolecular forces mean my particles are very strongly attracted to each other. So for me to pull them apart or to separate them, I need a lot of energy. So a high boiling point equals a lot of energy. A high melting point equals a lot of energy. And vapor pressure simply tells us the tendency to which something wants to evaporate. So if it's got a high vapor pressure, it tends to want to evaporate more easily at a given temperature. If I've got a low vapor pressure, it's harder for it, or it has a less of a tendency to evaporate at a given temperature. And this is because strong intermolecular forces make it hard for things to generally just evaporate, right? And then the weaker intermolecular forces will give you a low boiling point, less energy, low melting point, less energy, higher vapor pressure because it's more readily going to separate. I see Zizi's got a hand up. Let me quickly pause here and allow you to unmute and ask your question, Zizi. Okay, give me 2 seconds. I need to stop sharing to allow you to do that. Okay, Zizi, you can unmute and ask your question. Okay, Zizi, just hold on. I think I don't have my sound settings correct. Give me 2 seconds because I couldn't hear you. Okay, I can hear you now. Can you hear me, Zizi? Hello? Taffy, can you hear me? Okay, Zizi, you've muted again. I'm gonna carry on and then you can put up a hand if you remember what your question was, or you can post your question in the Q&A. That's fine. Okay, cool. Let's continue, guys. Let me just pull up my Q&A so I can still see everything there. Zizi says, please, can you explain using a graph? Zizi, I'll try and find a graph. I don't necessarily have one right now in front of me, but I'll try and see if I can find one to help you there. Okay. Okay, can we always use a table um, including 0 and 100 degrees? It depends on Olutu. It depends on what you're given as your melting point and boiling point. I was giving you an example. So if they give you a substance and say, here's my melting point and boiling point, simply just draw the same table out and mark out what your melting point is, what your boiling point is, and then find whatever temperature you're looking for, see where it fits. If it's lower than melting, solid. Higher than melting but lower than boiling, it's liquid. If it's higher than boiling, it's going to be a gas, right? How does molar mass affect surface area or surface area have an effect? We're going to cover that now as we do our question. Okay. All right, Blessing, I hope that helps. Let's jump into the next question. All right. So we're going to go and do a question quickly together. And then a lot of your questions will be answered as we go through this question, right? So the first question we're going to jump into is going to be question 3, which starts just above here, actually. Awesome. So question 3 says, learners investigate the boiling points of 4 organic compounds given below. So the organic compounds we've got there, we've got butanon, butane 1-ol, propanoic acid, and 2-methyl propan 1-ol, right? And now that we've got those there, we're given the molar mass, but butanon is 72 grams per mole, and everything else is 74 grams per mole. 3.1 says, define the term boiling point. That's what I want you guys to quickly do. Um, Type in the chat, how do we define a boiling point? Thank you, Blessing, for your quick fingers there. Thanks, Gabalo, for quick fingers. Okay. Just going through the chats. Tandiwe says, please re-explain solid, liquid, and gas. So Tandiwe, I've done the explanation about twice now. Our sessions are being recorded. So 48 hours from today, we'll post this lesson on our YouTube channel and share the link in our WhatsApp community. So I think take the time to go back and just rewatch the lesson. You'll find it'll probably be quite helpful. Okay, so let's look at our answer there. So the answer for 3.1, right? Define the term boiling point. It's the temperature at which the vapor pressure of a particular compound equals the atmospheric pressure. If you got that answer right, give yourselves a massive round of applause. Whatever way you want to celebrate in the chat or the reactions, give me a dancing emoji, give me a fire emoji, give me a heart emoji. If you didn't get it right, but now see where you went wrong and understand, that's also room to celebrate. Make sure you guys catch all those small wins every single time. While we're busy with that, Nolutando, you've got a hand up. I'm going to ask you to unmute and just ask your question. Nolutando, you can unmute and ask your question. Nolutando, I'm going to give you a few more seconds to please just go and ask your question. If not, we're going to move on and then you can put a hand up again a bit later. Okay, Ezra, in the Q&A, you said please check the chat. I'm not sure what specifically you want me to check in the chat. So if you have a particular question, just type the question in the Q&A and I can see it. So the chat of often, it gets inundated. There's a lot of us in this lesson, so a lot of stuff happens. Oh, you're saying it's all good? Okay, cool. I hope you got answered, Ezra. Thank you so much. Fantastic. Let's look at the next point, 3.2. So 3.2 then says, which compound, butane 1-ol or 2-methyl propanol, will have the higher boiling point? Fully explain the answer, right? So now what I want you to think about here is to think about the structure, right? So when you think about the structure, um, depending on the substance. So remember what I was telling you guys earlier. I'm going to tell you about different types of intermolecular forces and how they interact. So sometimes you'll have a long chain length. Sometimes you'll have a shorter chain length, right? How does that actually affect my molecules? So think about it. I always like to think about it in terms of Velcro. I hope you guys know Velcro. Remember when you were kids and you had those shoes that go and they didn't have laces yet, but it's just that thing that keeps your shoes tied together. It's that little carpety looking thing that's very sticky. That's Velcro. Now think about Velcro. Velcro, if you had a very small piece of Velcro, right, that looks something just like this, it's probably pretty sticky. But if you were to imagine a piece of Velcro the size of, I don't know, a table, and you had Velcro on, you would probably be able to stick to that table your entire body. But if you had a small 1 centimeter piece of Velcro, that couldn't hold you up at all, right? So the longer the chain length, think about that as you've got more points, right, to interact with another particle. Whereas if you've got a branched molecule, right, you've got less surface area. So the more surface area you have, that means you've got more points for your intermolecular forces to actually act on. So the longer your chain, right, it means you've got more points for that intermolecular force to actually act on versus the same molecular formula, but a way more compact molecule. The compact molecule really struggles in compared to the long molecule in terms of being able to attract the molecule next to it. So it's going to be harder to overcome the long chain than it is to overcome the compact chain. That's my little hint for you guys. Now with that, I'm going to come back to the question. Which compound, butane 1-ol or methylpropanol, will have the higher boiling point? If it helps, draw the molecule out yourself, right? Draw the molecules out to see what they look like, to see which one has the longer chain. And if you were there yesterday, you don't need to draw it out. Look at the name, right? You've got butane 1-ol, you've got methyl propanol. So you already can tell which one is going to be longer, which one's going to be shorter. But quickly have a look and then you guys can tell me what your final answer is. Kamano says, please give us 2 minutes to answer the question. I will give you guys time to answer this question, Kamano. So for those who've just joined us, welcome to the Learning Spaces Winter School, where we're going to be helping you guys to really get to terms with some of the topics that we are covering that are going to be big topics in your prelims. We do encourage lots of interaction and lots of participation. So please make sure to use the chat function, use your reactions, and use your Q&A. If you're joining us on TikTok for the very first time, welcome, welcome, welcome from the Learning Space family. Please click that follow button and make sure you are following us. We've got lots of awesome content on TikTok. We've got lots of awesome content on YouTube. So follow those up and then make sure you join us for the rest of winter school. If you're joining for the first time today, we're here up until next week, Tuesday. I think this earlier on today, we had a math session and today we've got a science and now we've got a science session. Tomorrow, the same thing will happen. We're going to have a double session, a math session at 3 o'clock and then a science session at 6 p.m. So make sure you guys join and then share the link with your friends, guys. We want to share the love and make sure that everyone is able to pass and pass really well. Awesome. I think the 2 minutes is up. So let's look at how we can compare these two, right? So it says there, which compound, butane 1-ol or 2-methyl propanol, will have the higher boiling point? Fully explain your answer, right? So you're going to get 1 mark for saying which one, and then the other 3 marks are for you to explain. So when you think about that in your exam, so I need to give 1 mark for the right answer, then I need to give 3 points to get the rest of my 4 marks. So let's quickly figure out which one is going to have the higher boiling point, and a lot of you have already got that right. In the chat there, it's going to be butane 1-ol, right? So that's your first mark there. So butane 1-ol will have the higher boiling point. Why? We need to give 3 points as to why that is going to be. So my 3 points are, number one, butane 1-ol has a longer chain length, right? So it has a longer chain length. Right? And what does that mean? So if it's got a longer chain length, I told you guys that there's more points, right, for London forces to take place, which means the intermolecular forces will be stronger. So the intermolecular forces for butane 1-ol will be stronger. If you're still unsure as to why they'll be stronger, I'll put that there again. There are more sites for London forces. Right? So again, remember, like I showed you guys here, the longer chain molecule is like a big piece of Velcro versus a small piece of Velcro. The big piece of Velcro has got more surface area for the intermolecular forces to act rather than the compact molecule. So the first thing has a longer chain. What does that have to do with anything? It means there are more sites for London forces to act, meaning the intermolecular forces will be stronger. And then the last point I need to then give there is that more energy is required to overcome the stronger intermolecular forces. So then finally, more energy is required to overcome the intermolecular forces. And like I said, guys, it's very important in that case there. Once you've seen that happen, you know that I said there's 1 mark for the answer, and then you get 3 marks for each of the 3 points you used to explain right afterwards. Okay, I'm going to pause quickly for any questions and then we will pick up right again. So, okay, come on, I've already addressed that. Okay, so Annalisa says, so if we are given a question of about 4 marks in organic compound and their molecular masses, are we allowed to start explaining how long the chain is or their branches, its intermolecular forces and their energy? Is it a must that we say weak or and not less energy when comparing compounds? I'm asking because I lost marks in my exam and I did not understand why. So in this case here, right, what you're going to do is you're going to be, first of all, say which one is going to be better. Then the first thing you need to do is be able to identify why, right? So the first reason is why. Longer chain length. Okay, what does the longer chain length have to do with anything? The longer chain length means that I'm gonna have stronger intermolecular forces compared to the weaker chain length. That's your second point. Okay, then what do stronger intermolecular forces have to do with anything? Well, stronger intermolecular forces means I need more energy to overcome them. And like I mentioned in the intro of this lesson, needing more energy means I need a higher temperature, higher boiling point, higher melting point across the board. And Elisa, I hope that makes sense for your question there. And then another question there from Zach says, sorry, sir, just need a quick reminder. Does the 1 in butane 1-ol represent where the O is? So the 1 in butane 1-ol tells you where the functional group is, right? So butane 1-ol is an alcohol. So the 1 tells you where do I find my hydroxyl group, my OH in butane 1-ol. I find it on the first carbon out of the 4 carbons. Hope that makes sense there. Kamana says, don't we need to explain the strength between the two? In this case, because we're comparing the two, Kamano, saying it's longer, saying it's stronger, it's automatically against the other one. What you could have done is you could have just said, 2-methylpropanol has a shorter chain length, which has weaker intermolecular forces and thus requires less energy to break the bonds. You could have spoken from the other side of it and you would have gotten the marks. So already saying stronger, longer, more energy, it's more energy against the second one. It's already implied in that case. But if you can write it out in full, Kamano, go for it. Because in this case here, you're going to really do well. Awesome. Okay, another question there says, why London forces instead of dipole dipole? That's a great question because you're reminding me now, because I said I was going to mention how some molecules have multiple types of intermolecular forces that they can actually interact with. So let's draw out those molecules, right? Butane 1-ol. So butane 1-ol is going to look as follows. So we're going to have 1, 2, 3, 4, and then we're going to have our OH on our first carbon. So let's just put that there. And then we're going to have hydrogens everywhere else. Okay, that's butane 1-ol. The other molecule we were told was 2-methyl propane 1-ol. Okay, so let's quickly do that. I'm gonna cheat a little bit and copy some of this off. Okay, and there's 2-methyl propane 1-ol, which means here I'm gonna put a methyl group, CH3. And then it's propane 1-ol, meaning the OH is going to still be on my first carbon there. All right. So one thing I want you to notice, right, is now, remember I said this OH is going to be a site for hydrogen bonding to occur. So wherever you see this OH, that's where hydrogen bonding can occur. I'm going to take a quick and the oxygen. It's actually not, right? Very important. That is not a hydrogen bond. Very important. The hydrogen bond happens between two molecules that have that type of bond between them. So if I've got something with an H and an O, remember when I've got that happening there, the reason why we've got hydrogen bonding is because the electronegativity difference between oxygen and hydrogen is quite high. So the oxygen becomes slightly negative, my hydrogen becomes slightly positive, right? And then when you've got another molecule that's going to be similar, let me quickly do this and duplicate and turn it around, right? In this molecule here, remember, oxygen is slightly negative, hydrogen is slightly positive. The attraction becomes between the slightly positive hydrogen to the slightly negative oxygen in the other molecule, as well as the slightly negative oxygen and the slightly positive hydrogen in the other molecule. This right here, that is what our hydrogen bond is. It's the intermolecular force between two molecules where hydrogen is bonded to nitrogen, oxygen, or fluorine. So that is the hydrogen bond there. So when we come back and look at our molecules, let's look at that butane 1-ol. On this side of my butane 1-ol, that OH allows me to interact with dipole-dipole. It also allows me to interact with hydrogen bonding, this side of the molecule. But remember now, the other side of my molecule it looks like an alkane. It looks like just a pure hydrocarbon, which means on this side, I can actually engage with London forces. Because that side of the molecule, I can go attract other alkanes, other alkenes. So one molecule can engage with more than one intermolecular force. That's why if you go back to the notes I showed you, let me quickly go back there, right? The note said, what is the primary intermolecular force? The operative word there being primary, because you can get more than one intermolecular forces in a molecule, but there's going to be one primary, which is going to be the strongest one that that molecule can essentially work with. So for alcohols, the primary intermolecular force is going to be your hydrogen bond, but you can have London forces as well. That's why when we're comparing butane 1-ol and 2-methyl propanol, they both have hydrogen bonding. So hydrogen bonding is equal. You can't really compare them. So that you have to look at the next criteria. The next criteria is if the hydrogen bonds are equal, what happens next? Well, the next thing is let's look at the chain length. And butane 1-ol has a longer chain than methyl propanol. And in that case, the chain length wins, and chain length is a function of London forces, not hydrogen bonding. I hope that makes sense to you guys. I know it was a very long, roundabout way of explaining that, but it becomes very important that we understand it. Okay. Cool. Why London forces? I've already answered that one. Isn't that alcohol has one side for hydrogen bonding? Yes, but I feel like I've already answered that now as well. Will we reschedule for today's business? Because it seems as if yesterday's continuation is taking over. This is anonymous attendee. So, anonymous attendee, as we've mentioned already. So, we're moving all the topics down by a day, essentially, right? Because I was going to do the continuation next week, but the request was because we've already started, let us just continue. So I'm going to continue with yesterday's lesson today, and then what was meant to be done today will be done tomorrow. What was meant to be done tomorrow will be done on Tuesday. So just make sure you stay tuned, and then I'll ask the team just to communicate that as well to you guys. And then Ella says, will you be able to send us a document? 100%. As soon as I'm done with organic chemistry, I'm going to package those notes and send them through to you guys. You'll have all my notes and all my writings up. Okay. And then I don't understand why it's not a hydrogen bond. Gabby, so I hope that makes sense. So hydrogen bonding is there with alcohols. The key thing is that we're comparing two alcohols. So it doesn't make sense comparing two hydrogen bonds, right? Because they're going to be the same essentially. No one hydrogen bond is stronger than the other hydrogen bond if they're both OHs. So we have to compare something else that's not a hydrogen bond. So we're going to compare the other side of the molecule, which is the London forces side of the molecule. And that's how we then compare the two molecules. Awesome. Let me quickly go into the chat and then we can, once done that, we can just quickly move on with this question. Okay, thank you for these are all answers. Link for tomorrow will get sent to you. Um, Someone's asking there if you said surface area. If you said surface area, that's fine, but you must link surface area to the chain length. That the chain length gives you greater surface area for your intermolecular forces to interact essentially. Okay. Um, Yeah. So someone did say, as are there, ask questions in the Q&A because I do see it quicker. In the chat, guys, please note there are a lot of you guys in this class right now. So the chat I normally leave for when I ask you a question, respond in the chat. If you've got an important question, put it in the Q&A. Because then your questions will get lost in the chat. So give me answers in the chat and then ask questions in the Q&A. Thank you, Ezra, for that. You're my new class captain, Ezra, by the way. Okay. And then a lot of the same questions, and I've kind of gone through them there. Okay, if I've missed your question, please just re-ask it in the chat. But I have pretty much tried to answer everyone that someone's put out there. Ratabel is asking, do you have a WhatsApp group? Yes, we do have a WhatsApp community. The link was shared earlier. We will share it again later on in the session. Awesome. Let's move on to the next part of the question. So that was 3.2. Then we're going to look at 3.3. So, sorry, before I move on, Karabo says, am I wrong to say more energy is required to overcome the bond? Karabo, you are not wrong. That is required to give you your marks. So let me quickly recap everything you need to put down to get your marks, right? Um, so in this case there, butane 1-ol, you had to give the one that you thought would work. The next thing, so butane 1-ol has a longer chain length. That's mark number 2. The intermolecular force will be stronger, or you can say greater surface area for London forces. That's point number 2. I mean, that's mark number 3. The last mark, you must say that more energy is required to overcome intermolecular force. So that point, Karabo, is required to get all of your marks. Well done for that. Okay. And then Untatila says, can you also consider the molar mass while comparing the two? So let's go look at the molar mass, right? So when we're looking at butane 1-ol and 2-methylpropanol, let's quickly look at their molar masses. So butane 1-ol is over here with 74 grams per mole, 2-methylpropan 1-ol, also 74. So you can consider it Untatila. The challenge is the molar masses are identical, similar to the whole story of the hydrogen bonding. They've got the same type of bond. So if they're the same type of bond, you can't compare. There's no clear winner. Molar mass, identical. There's no clear winner. So you have to go to the next level, which is what other intermolecular forces are there? In this case, when you look at the structure, I've got one side, which is a site for dipole-dipole or hydrogen bonding in particular, and I've got the other side, which is a site for London forces to bond. So let's compare the London forces, and you can see butane 1-ol has got a longer chain than the propanol, so therefore the butane 1-ol will have the higher boiling point because that's going to be higher intermolecular forces and more energy is required to solve it. Okay, awesome. Hope that helped, guys. Let's jump straight into last one there. Someone says, can I explain primary, secondary, and tertiary while you're at it? I did that yesterday, Tapelo. You'll find it in my notes and you'll find it in the recording of the original lesson, right? Blessing Lewis says, if you spoke about surface area in relation to side chains, are you wrong? No, you're not wrong at all. So you must talk about that surface area because as long as the surface area is in relation to the points or the sites for intermolecular forces to interact. So when you say I've got more sites for London forces or less because it's a longer molecule or less compact molecule, you're doing really well in that case there. Always link surface area to the intermolecular forces. Don't just talk about it by itself, right? Awesome. Okay, let's quickly jump on to the next one. I need to move to organic reactions at 7 o'clock. All right. So the curves PQ, R, and S below were obtained from the results of the investigation. X represents a specific temperature, right? Cool. Then 3.3 says, which physical property is represented by temperature X? Please quickly put that in the chat. Which physical property is represented by temperature X? Quickly pop that in the chat. If you're joining us on TikTok, please make sure to engage with us. So put down what physical property do you think is represented by X? So the question isn't asking for what is the temperature at X, but what is the physical property? Thanks, Louis. Thanks, LT. Thanks, Leletu, and everyone for their quick fingers. I'll give you guys some time to think about it. 30 more seconds. Don't panic if you haven't finished thinking about it. Hope says, what about the position of the functional group? So the position of the functional group doesn't really have much of an effect. What whether you have a branched or an unbranched molecule or compound is more the thing. But the position of the functional group doesn't really change quite a lot. Okay, 10 more seconds if you haven't put your answer down. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay, a lot of you guys got it right there. So X basically represents the boiling point, all right, of compound P there. So X represents the boiling point. Let's quickly put that down, right? And how do I know that? So simply look at my graph, right? So remember, we've got curves that are obtained as the result of a particular experiment. So over time, I can see my temperatures are increasing. They increase and increase up to a particular point, right? So think about a liquid. It's like when you have a liquid in a container, the temperature can only go so high because once it goes above that temperature, so let's say water, once it goes above 100, it's no longer liquid water. It'll evaporate off. But all the water can be at maximum at a given temperature, at a given pressure, 100 degrees Celsius. So S, R, P, Q, they'll all level off. And wherever they level off, that is the boiling point of that particular substance. So X is going to be the boiling point of P in particular. But in this case, all they asked for is the boiling point. Um, Someone asked, Precious asked, why boiling point? I just explained that. I hope that makes sense. So when you're dealing with substances there, as the temperature increases, at some point the temperature will stop increasing because beyond that it boils off, and then the temperature will not increase. So it's like you can't have water in like atmospheric pressure. You can't have water at 200 degrees Celsius, right? Because above 100, it'll evaporate. So you can't increase the temperature of water beyond that point unless you change the pressure. But at a given pressure, the water will start evaporating and then you can't go any higher in temperature. That's why all of those graphs will level off. So X is the boiling point of substance P. All right, now let's answer the rest of it. 3.4 says which curve represents, then they ask you for butanon, propanoic acid, 2-methyl propane 1-ol. So let's have a look at them independently and then try and see um, by looking at the molecules, which one will have the higher or the lower boiling points, etc. Right? So looking at the ones we've got there, let me quickly just erase this there. I want you guys to look at that and tell me which one you think will have the highest boiling point. You can post that in the chat. So which one do you think will have the highest boiling point? Looking at the organic compound, think about its structure, think about its intermolecular forces. Which one will have the highest boiling point? And give me a reason. Give me a reason. So thank you for your answers there. Awesome. Awesome. I'm loving the answers that are coming through. I'll give you guys 30 more seconds to put answers through. If you are joining us on TikTok, please don't forget to put your answers in there. We really would appreciate it. What I'm going to do while you guys do this, I'm quickly going to grab my phone so I can actually see. I realize I'm not seeing all the questions that are coming through on TikTok. Awesome, guys. I'm back. Cool. So now we're going to go and compare them. So you guys said, a lot of you guys said propanoic acid, right? Um, you said it's got the highest boiling point of them all because it's got really strong intermolecular forces. Someone did even make the extra mention, which I like, of that it's got two sites for hydrogen bonding, which is really good. Okay. So what I want to do now is let's quickly go back and look at our questions, right? So we said, which one represents propanoic acid? You guys said is going to have the highest boiling point, right? So 3.4.2 propanoic acid. So I'm going to just do it that way. We can see the highest boiling point is P. So you guys are saying that 3.4.2 is P. And if you guys said that 3.4.2 is P, which is propanoic acid having the highest boiling point, you guys are very much correct, right? So one thing I want you guys to then find is which one is going to have the lowest boiling point. So let's quickly look at that. And I want you to tell me which one will have the lowest boiling point. Quickly pop that in the chat. I'll give you guys 2 minutes and give a reason as to why. Okay, I've actually got my TikTok notes here. Sorry. So apologies to anyone that I haven't seen. Thanks, Leslie, for your answers there. Thanks, Norma, for your answers, and Melissa as well. Okay, answers are coming in. I'm going to give you guys 10 more seconds. Five, four, three, two, one. So let me see. I'm seeing butanon. I'm seeing butanon. Um, Melissa says butanon. Leslie says butanon as well. Seeing a lot of butanon, right? So you guys said butanon has got the lowest boiling point. So let's quickly put that there. So you guys are saying, um, so you guys said propanoic acid was P. You're saying butanon was the lowest boiling point. The last thing I want us to compare then is the two that we haven't identified is to say which one is going to be higher. So we've got propanoic acid and butanon already covered for, right? That's covered, that's covered. So between butane 1-ol and 2-methyl propane 1-ol, we already discovered which one actually has the higher boiling point. We did that in the question. So butane 1-ol will have a higher boiling point than 2-methyl propane 1-ol. So we can quickly go back and write there. That's going to be the butane 1-ol, and that will be my propane 1-ol, right? So now we've identified everything on our graph, right? Once we've identified everything on our graph, we can now way more easily go and answer our question. Because then we'll get asked there, which curve PQROS represents butanon, right? Then we already said, oh, well, butanon is going to be S, so we can put our S there. Propanoic acid, we know we've already identified propanoic acid there. We put the P. 2-methyl propane 1-ol, we've identified that there. It's going to be our R, right? So that's a way that you can do these graph-like questions. Is first go, don't even look at the question. Come back and identify which one is which based on the information that's been given to you. Once you've done that, when you come and answer the question, it becomes super easy for you to be able to do that. Then they said, give a reason for the answer to question 3.4.2. The 3.4.2 is the propanoic acid, right? Which we said is going to have the highest boiling point. So for propanoic acid, which is the highest boiling point, right? Number one, we've got 1 mark there, so we can give any reasons. Any of the following reasons we can give there. So you can either say it's got the highest intermolecular forces, right? You can also say it's got 2 sites for hydrogen bonding. Someone had that there, right? And if you're asking me, what do you mean 2 sites for hydrogen bonding, right? Because it's a carboxylic acid, propanoic acid will be, let me quickly draw it like the C dash C dash C, double bond O and the OH there. So with all my H's there, remember, this side is my London forces side, and then here I've got my H bond side, right? So I can either H bond around the OH, I can also H bond around that double bond O, which is important. All right, cool. So that does help you in that case there. And then the last version of the answer you can just give, you can simply just say it requires the most energy to overcome intermolecular forces, right? Awesome, guys. And that's organic properties. I am 8 minutes late, but it's fine. We'll be able to push through for the last hour. Okay. Um, Liletu says, what type of intermolecular forces do esters have? Um, so esters will have by themselves dipole because they don't have an OH. So by themselves they'll have a dipole, right? Um, and then yeah, I think we are covered in that case there. Let me double check if I'm missing anything else in the chat. Okay, perfect. I'm quickly going to then jump into organic reactions for the last 50 minutes of the session. I need to go back to my summary notes for that. Sweet. And then we can wrap this section up, right? Okay. So when we're dealing with organic reactions, we have a few types of reactions we're going to be dealing with. So we've got combustion, we've got esterification, we've got addition, substitution, and elimination, right? So when dealing with oxidation of alkanes, or what we refer to as combustion. It's a reaction of alkane with excess oxygen to form carbon dioxide and H2O. We saw an example of that yesterday, right? So it's extremely exothermic reaction. It produces high amounts of heat, right? So example C5H12 with oxygen giving you carbon dioxide and water and lots of energy. Think about any fire you've started. Basically, what you're doing there, you are combusting essential hydrocarbons, right? So the best version of a combustion reaction that moves us every single day is what happens in a car. So most cars will have octane a version of it in the engine, and that octane will then be burnt up to create lots of energy that will drive the vehicle. And then we have lots of CO2, which is what causes our greenhouse problem and our heating problem, as well as water. Cool. Next up, we're dealing with esterification, right? So now, esterification, number one, you need to think about reaction conditions. Esterification requires an acid catalyst, for example, sulfuric acid, H2SO4, right? It's what we refer to as a condensation reaction, right? Where two molecules combine to form one. That's condensation. So generally, what you need alcohol and the carboxylic acid. Those come together to form an ester and water as a product. So what you guys can see there is when the two come together, right? You've got this OH and this HO in the middle. So, and sorry, let me quickly go back. Two H's and an oxygen will come off, and that gives us the H2O. And then from there, this molecule joins that molecule and gives you this right here at the bottom, right? So that's how esterification essentially just happens. And it'll always happen the same way, alcohol plus carboxylic acid giving you ester and water. Then we can look at an addition reaction. Addition reactions take unsaturated compounds and they undergo addition reactions to become more saturated. All right. Let me quickly pause for questions. Or can I quickly finish this? Then I'll come back and address the questions. All right. Please remember, guys, put your questions in the Q&A and in the comment section or the chat section, I'll come back and your answers must go there. But if you're joining us on TikTok, just put your questions in the chat. I'll check it out. So addition reactions is where we have things like halogenation, hydration, hydrogenation, right? So hydrohalogenation is when we're adding a hydrogen halide. So for example, HCl, HF, HI, right? Hydrogen bonded with anything in group 7 is our hydrogen halide. And you add that to an alkene to form a haloalkane. A key reaction condition there for the hydrohalogenation, no water must be present. Very, very important. Another addition reaction is going to be halogenation, right? Where we're adding a halogen. So, for example, chlorine, iodine, fluorine, bromine, to an alkene to form a haloalkane as well. This happens quickly and spontaneously, as in the bromine water test. Very, very important there. Then hydration is where we add water to an alkene to form an alcohol, right? So in that case there, you need excess water, so you need a lot of water and a small amount of a strong acid catalyst. So for example, hydrochloric acid, HCl, is a reaction condition. Then finally, you've got hydrogenation, where you're adding hydrogen to an alkene to form an alkane. So your alkene must be dissolved in a non-polar solvent with platinum as a catalyst. So these are all reaction conditions that you must then memorize. They do sometimes ask them, but they're not going to give you a big essay question on this particular part there. All right. Then we've got elimination reactions, which are basically the opposite of our addition reactions. So there you're dealing with saturated compounds that undergo elimination reactions to become unsaturated, right? So dehydrohalogenation. So if you think back to hydrohalogenation, we added a hydrogen halide. Dehydrohalogenation, we are removing a hydrogen halide. So for example, hydrogen fluoride, HF, is removed from a haloalkane. This requires heat under reflux and then a concentrated solution of sodium hydroxide in pure ethanol. Very, very important. Sometimes they'll ask you, why do you need to do it under reflux? And then you'll see. I think the question we'll do might actually have that question, and then we'll see how we answer it there. Then we had hydration, now we've got dehydration. Hydration, we added water. Dehydration, we are removing water, right? So H2O is removed from an alcohol. What you need there is it's going to be an acid catalyzed reaction. So alcohol must be heated in excess, with excess concentrated sulfuric acid, H2SO4. Another type of elimination reaction we've got there is what we refer to as cracking, right? Where cracking is where we take long chain hydrocarbons and we break them down into shorter hydrocarbon chains that are way more useful to us in life. So you have catalytic cracking and thermal cracking. Catalytic cracking has got low pressure and temperature, and then use a catalyst. Thermal cracking has got high temperature and pressure, and we don't use a catalyst there. Then finally, we're dealing with substitution, right? So in substitution, the hydrolysis of alkanes, okay? So again, hydrolysis of alkanes talks about taking haloalkanes and reacting them with a strong base, for example, potassium hydroxide, sodium hydroxide, to form alcohol and a hydrogen halide in that case there. And then the haloalkane is dissolved in ethanol and reacted with dilute weak base and mild heat. Then you've got halogenation of alkanes. So you can take a halogen, for example, iodine, bromine, fluorine, add that to an alkane to form a haloalkane. This requires heat or UV light. So as in the bromine water test, bromine reacts slowly with alkanes and quickly with alkenes. Use this test to see if something is saturated like an alkane or unsaturated like an alkene. Someone asked this question yesterday. I was hoping we were going to get to this point, but then we didn't quite get there, but today we are there, right? Cool. And then finally, alcohols to haloalkanes, right? So reacting a hydrogen halide with alcohol to form a haloalkane, we use hydrogen bromide or hydrochloric acid at room temperature. This is best done with tertiary alcohols. And then someone asked the question, what's the difference between a primary, secondary, and tertiary alcohol? Essentially, in a very short answer, I'll tell you now, I drew it somewhere there, or on the next page, right? A primary alcohol is an alcohol where your hydroxyl group is connected to a carbon that's linked to one other carbon. Secondary is where your hydroxyl group is on the carbon that's connected to two other carbons. Tertiary alcohol, your hydroxyl group is on a carbon that's connected to three other carbons. That's primary, secondary, and tertiary alcohols. These notes will be there. People keep asking the question. We will share them in our WhatsApp community as soon as we're done with a particular topic, right? Now we've got 45 minutes left. Let's quickly try bomb through the question that we've got here for organic reactions. Hope you guys are ready. I'm going to pause for questions just before I start the question four. Okay, so in this case here, can you send the notes in the group? Definitely anonymous, we will do that. So can you please show how to balance the equation of combustion? We did that yesterday. So if you just go watch the recording, you'll see how we can do that. Otherwise, just like there's lots of questions on balancing equations. What I often tell you is leave the oxygen for last because oxygen is always by itself. It's the easiest to balance. So balance everything else first and then leave oxygen for last. I hope that helps you, Anonymous. And then you also said, may you please go back to combustion for a second? I missed something. I like to see what I missed. I'm gonna share the notes on this section. So is it fine if I do that and then continue? I don't want to just miss finishing the question again today because I can't extend another session. We have to kind of keep it going. Apologies for that. And then Leletu says, is there a way to remember all of these reactions easier, similarly to Ibomeva? Oh, I wish there was. I think we need to find that teacher and ask him to make up one for organic reactions. The best thing I can tell you is just keep in mind, esterification and combustion, they sit there by themselves. The three key reactions are addition, elimination, substitution. Addition, I change my saturation. So addition, I go from less saturated or unsaturated to saturated. Elimination is the opposite. I go from saturated to unsaturated. Substitution, I don't change saturation at all, right? Then what I add is the name of what I'm dealing with. If I'm adding hydrogen, hydrogenation. If I'm taking it away, dehydrogenation. If I'm adding a halogen, halogenation. Taking it away, dehalogenation. If I'm adding a hydrogen halide, hydrohalogenation. If I'm taking it away, dehydrohalogenation. If I'm adding water, that's hydration. Taking it away, dehydration. That's how I normally remember it. And then you'll basically see it there. Someone says use the Kevin Math Science map. It'll help with the reactions. I'll try find, there's another map that I had somewhere. I'll try see if I can find that and share that as well. But essentially, it's at the end of the day, it is a map. It still needs you to go and ingest it, put it in, understand it, and utilize it. For me, the best way is do lots of practice and you'll get a sense of how this stuff all works, right? Kiamogeto says, hey, sir, if a hydroxyl group were, sorry, so if a hydroxyl group were to be bonded between two carbons with a third one based um, on the bonded carbon, is it a secondary or tertiary? Kiamogeto, I have to see how that would be structured. Um, because the hydroxyl group can't be bonded between two carbons. It can only be bonded to one carbon. Then the carbon with the hydroxyl group, look at how many carbons it's got. If that carbon has one carbon next to it, primary. If that carbon has two carbons next to it, secondary. If that carbon has three carbons next to it, tertiary. That's how basically you need to look at it, right? Okay. Awesome. Let's start question 4. So we actually managed to finish today's work, right? Okay, let's jump straight into it. Someone says, will you guys please explain the SSS thingies in full? I'd love to do that for you guys to do that as well. I'm not sure what you exactly referring to, but maybe someone can post a link. Someone said it's on YouTube. Maybe just post a link in the chat for us. Cool. Question 4. Let's jump straight into it. It's a little bit of a long one, so let's try be a little bit patient, right? So it says here, the flow diagram below shows different organic reactions, P, Q, and R. Um, um, sorry, different organic reactions, full stop. P, Q, and R are organic compounds. So we see there we've got alcohol P, reaction 4 takes place to form compound Q. From compound Q, reaction 1 takes place with bromine to give you 1,2-dibromo 2-methylpropane. Then also reaction 2 from compound Q takes place with HCl to give you a major product compound R. So that major product part, we haven't actually touched, and I think it's important that we do touch it. So whenever you're dealing with addition and elimination reactions, we've got a rule, or actually two rules, called Markovnikov and Zaitsev rules, right? Zaitsev's rule. So these two rules basically say when undergoing an addition reaction and you have to give hydrogens somewhere, give hydrogen to the carbon with the most hydrogens. And when eliminating, and you have to take hydrogen away from the carbon with the least number of hydrogens. If you follow those two rules, you will get a major product. If you don't follow those two rules, you will get what we refer to as a minor product. So when they say major product, they're saying when given the choice, always give hydrogen to the carbon with the most hydrogens and always take hydrogen from the carbon with the least hydrogens. Okay, awesome. So then let's start there. Question 4. Reaction 1 is an addition reaction. Write down the type of addition reaction. I want you guys to post this in the chat. What type of addition reaction do we have in reaction 1? Here's the hint. Look at what we are adding in this reaction. So reaction 1 is an addition reaction. What type of addition reaction it is? Is it? Okay, lots of answers coming in. Thank you so much. I'll give you guys 10 more seconds. Okay, someone on TikTok asking what grade this is. This is grade 12, organic chemistry. Okay, 5, 4, 3, 2, 1. Well done for those that have put the answers in. We're adding bromine, which is in group 7. This is halogenation, right? So halogenation is our answer. Okay, halogenation. Then 4.1.2 says, write down one observable change which occurs in the container during the reaction. So when reaction 1 happens, name one observable change we can see there. So what happens in that case there? So we've got compound Q, we add bromine, and then we end up with 1,2-dibromo 2-methylpropane. So what do we see there? LT says change of color. I want you to be a bit more specific. But I'll give you half a point, LT. Be a little bit more specific. Thanks, Cabello there. Thanks, Rtabile. Okay, they give you guys 15 seconds to think about it, right? Think about what color is bromine naturally, and what happens when I'm gonna add bromine to my vessel. It's an addition reaction. In my addition reaction, what happens to the bromine? Do I get more bromine or less bromine? So tell me about what that color, what happens. So don't think about what happens when I add bromine in. Think about when the reaction takes place. Okay, 5 more seconds. 3, 2, 1. Okay, so the key thing there, right? An observable change. So remember, bromine itself is going to be like a brown reddish color. But as the reaction takes place, it's an addition reaction. What happens in my addition reaction? My bromine is going to react. It's going to basically I'm going to have less and less and less bromine in my vessel as my reaction takes place. So the color that's going to change is going to be from the brown reddish color and it's going to become a bit more clear, essentially, right? So basically, I'm going to start off brown reddish. So the brown reddish color will disappear. That's the key thing. So don't think about what color bromine is. Remember what happens when the reaction takes place. When the reaction takes place, my bromine is reacting out of my vessel. It's becoming part of this 1,2-dibromo. So as my bromine in its normal state comes out, the dark color goes away, goes away, goes away, goes away. Okay. Garabo says, how do you know about the color? Is it from the notes? It's not from the notes. I think it's just a general thing from science that you've been learning when you've been doing experiments. Like bromine is brown, permanganate, potassium permanganate is like purple, copper sulfate is blue. There's general colors through experimentation that you just get to know, essentially, right? Okay. Hope that helps there, Garabo. Cool. 4.1.3, give the structural formula of compound Q. So let's first see there, right? So compound Q, we basically had this here, but this comes from that compound. So basically, I need to essentially just take away my two bromines and then I'll be able to have compound Q. So how I do questions like this, I'll start with what has been given, I'll draw that, and then I'll say, well, if I remove my bromine, what is left? So let's first do that. So we're going to first draw our 1,2-dibromo 2-methyl propane. How do we draw that? Remember, whenever you're drawing, you start at the end and work your way to the beginning, right? So I know I'm dealing with a propane. So propane is going to be 1, 2, 3, right? Then let's go next thing there. I've got a methyl on the second carbon. So that's going to be CH3 there. And I've got 1,2-dibromo. So then my 1,2-dibromo, I'm going to have bromines on the first carbon and a bromine on the second carbon as well, right? So now that I've got that, that is what my final product was. The product before that didn't have a bromine, and I was told it was an addition reaction, meaning where my bromines are was just a double bond. So essentially all I need to do there is remove these guys here, add a double bond, and then complete my diagram. So in this case here, and then just put H's everywhere. 1, 2, 3, 4. Nope, this has got too many H's. There we go. And then all my H's there. Okay. And then there you should have your molecule. This is compound Q. Hope that makes sense. I'm going to pause for questions quickly. Mpo says the screen is not clear. Mpo, I think your connectivity might be dropping. Just if you using Wi-Fi, try move closer to your router. If you're using 3G or 4G, try move around a little bit until you get a slightly better connection. Closer to a window will help. Naledi's asking, why is it a double bond? So remember, Naledi, we were told that reaction one is an addition reaction, right? Addition reaction takes an alkene and makes an alkane. So I started here, worked my way back. I know I must start with an alkene because alkenes have double bonds. I can't do an addition reaction unless I've got an alkene. That's how I use a double bond. Then one more question there. Lewis says, um, do we consider the physical properties such as odor and solubility of the compounds? Not so much in organic chemistry. Odor is like, all you need to know about odor is that esters have odors and essences and tastes and stuff. They're used for that. You don't need to go and consider specific odors of specific things because also describing odors can be a little bit tricky. I hope that makes sense. Um, Garaba says, can you please send notes about the colors of bromine, etc.? lost in terms of that. I'll try and find some. I don't necessarily have notes right now that go through all the colors of everything. Like I said, bromine is like reddish brown. Copper sulfate is like blue. Potassium permanganate, I think, is like purple. Um, Magnesium flames are bright white. There's like just general chemistry things that need to be there. I'll try and find something about the colors within chemistry and then see if I can share it. I can't promise. I don't know if that single resource exists in that format, right? Okay. Awesome. Let's move on to the next question. So then it says, consider reaction two, right? Write down the IUPAC name of compound R. So let's look at reaction two. Reaction two takes that same compound Q that we just had right there. So compound two basically becomes 2-methylpropene. So 2-methylpropene undergoes a reaction with HCl, and we then look at the major product. All right. So we look at the major product there for for 4.1.4, they want the name of compound R. So we need to think about then what's going to happen there with compound R, where we take that and add HCl. So let's quickly see what's going to happen in that case there. I'll do it right next to this one. So if we had, can I copy this actually? Let me see if I can copy this. Is my whole page moving? My whole page is moving. Okay, I didn't want that to happen. Okay, let me just, it's fine. I'll just draw it again, right? So in this case here, so I've got C double dash C dash C dash H dash H dash H dash CH3, right? And then here I've got two hydrogens. In that case, they 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Perfect. So now that molecule that we start off, that's compound Q. We react that with HCl. What's going to happen? So it's going to be another addition reaction. In this case here, we're adding HCl. So when that happens, what's going to happen? We're going to first break this double bond, right? And then we're going to leave a bond here and a bond there. One of those will get the H, one of them will get the Cl, right? Then remember, they asked us for the major product. What did I say about major and minor products? Major products follow Markovnikov and Zaitsev's rules. When giving a hydrogen, give a hydrogen to the carbon with the most hydrogens. When removing hydrogens, remove hydrogen from the carbon with the least number of hydrogens. So in this case here, if I'm giving a hydrogen, I'm going to give it to the hydrogen, to the carbon on the left. It already has two hydrogens. The one on the right has no hydrogens. So then what's left for me there to do is my Cl was going to go in this place here. That's what we've got there. Now we need to just name this substance, right? So in this case here, we start with all the side chains that we've got there. So what side chains do we have? Let's quickly find them. So we've got a chlorine there and we've got a methane there. So we're going to have a chloro and a methyl. So the first thing we're going to put down there is chloro and methyl. And before I get too far, I need to number my carbons. So numbering my carbons, I'll have carbon 1, 2, and 3. In this case, it's a haloalkane. The order doesn't matter because my functional group is right in the middle, right? So then when it comes to naming this thing, start with the side chains. Chloro and methyl, remember they have to be in alphabetical order. So I'll start with chloro, then I'll do methyl afterwards and specify where it is. So I'm going to have 2 chloro, right? And then I've got a methyl also on the second one, 2 methyl. Cool. Now to finish it off, what molecule am I dealing with? What's my longest carbon chain? My longest carbon chain is 1, 2, 3, right? Whichever way you look at it, this is a propane, all single bonds. Then I can finish off my answer by saying methyl propane. Okay. If you are struggling with naming and drawing substances, please go watch the recording when we've got it up of yesterday's session, where we spend a lot of time naming, doing IUPAC names, and drawing molecules. So I'm not going to spend too much time on this one because the question is still a little bit long, right? All right. So that's the IUPAC name of compound R, 2-chloro-2-methyl propane. Hope that makes sense. I'm going to pause for questions quickly. Okay, when are we going to do energy and chemical change? That's a grade 11 topic, Lue. It'll probably be covered sometime in term three. So we're going to start a grade 11 session as well in August going forward. So we'll do that. Bongeka says, when can we get the recordings? So the recordings will be on our YouTube, but we will also send you guys links, everyone that was there. Okay. And then everyone else was giving answers to chloro 2 methyl propane. Well done to everyone. If you got that answer right, give some great reactions. We haven't been reacting in a while. I think I even forgot about that. There's so much content. Give some great reactions there. Fire emojis. The more creative, the better. If you didn't get it right, but see where you went wrong, also celebrate because that means you learned something today. And that's very, very important, right? So you must celebrate everything that you learn. Okay. Tebogo says you didn't send notes yesterday. Tebogo, I'm very much aware. So what I wanted to do was to finish organic chemistry so that when I send you the notes, they're complete. I don't want to send you two separate notes and then you must deal with different things. So today we're going to finish organic chemistry, then you're going to get completed organic chemistry notes. Cool. Thanks for all the celebrations, man. You guys are amazing. You guys are awesome to teach. I wish I could teach you every day. I really enjoy it. Okay, so let's now look at 4.1.5. For reaction 3, write down a balanced equation using structural formulae for the organic compounds. Let's go have a look at reaction 3. So reaction 3, right, we take the major product, what we've just created, the 2-chloro-2-methyl propane, and we react that somehow, and we end up with an alcohol, right? The first question I'm going to say to you, what other substance do we need for reaction 3? Quickly put that in the chat. So to go from where we were, which is 2-chloro to methyl propane, to create an alcohol, we need something, right? So don't think you can think reaction conditions, you can think whatever, but there's something we need for this to take place. Quickly put that in the chat. Okay, Fezaga and Nintendo, I want you, that's half the marks. I want you to give me a complete thing, right? OH doesn't just come by itself. So give me a complete thing. Okay, thank you for all the answers. I'll give you guys 20 seconds to still think about it. Don't feel any pressure. Even on TikTok, please drop your answers there. We want to take this 2-chloro, 2-methyl propane, and we need to create an alcohol, but we're missing something. So what are we missing? We need to add something to this to get our alcohol. Quickly put your answers in the chat there. 10 more seconds. Bonus points if you tell me what kind of reaction this is. Addition, substitution, or elimination. 5, 4, 3, 2, and 1. Well done. A lot of you guys got the right answer. There's a number of things we can use, right? So we can use a strong base or we can use water. So strong bases, think group 1 hydroxide, sodium hydroxide, potassium hydroxide, lithium hydroxide. Those are all strong bases. Or you can even use water. That will also be accepted, right? So let's quickly do that that they've asked us to do. Balanced equation using structural formulae for the organic compound. So we're starting off with originally what we had. So what we had was our chloromethyl propane. So that's going to be C dash C dash C dash Cl dash CH3, and then fill up our hydrogens everywhere else. Okay, that's what we're starting with. Then we need to add, so what we're going to add, you can either put sodium hydroxide, potassium hydroxide, lithium hydroxide, or even water, right? So you can either put the your NaOH, you can have your KOH, you can have lithium hydroxide, right? You can even have your H2O as well there. So any one of those will give you the mark. Don't put them all, put either or. Okay. Once we've done that, we need to think about what is going to happen. It's a substitution reaction, right? So what am I going to remove from my first structure? So what am I removing to put in my OH? To get my alcohol in, what am I removing? Quickly put that in the chat. From my chloromethyl propane, what am I removing? Thank you for all the quick fingers there. You guys are awesome. TikTok group, you guys are falling behind. My Zoom guys are gonna nail their prelims. So we need to compete a little bit harder there, right? Okay, thank you for all the answers. We're gonna basically remove this chlorine and we're gonna put in either that OH, that OH, that OH, or this OH over here, right? Cool. Thanks, Melissa. Thanks, Nisha. And then all we need to do is just redraw that with OH in place, right? And then we'll then have our C dash C dash C. Down here is our OH. Up there is our CH3. And then we've got our H's up here, H's everywhere there. And then we're going to have another product. So what product are we missing? So if you gave me NaOH or you gave me H2O, we need to have another product, right? Because essentially what happened there? I took the C out and I'm gonna have this or this or this or that left over. So depending what you took out, you're gonna have something left over, which is some kind of salt, right? So you'll either have sodium chloride, potassium chloride, lithium chloride, or even HCl, right? Someone there said HBr. Can't be HBr because we didn't have um BROH as one of our options, right? So it's going to be either be NaCl, KCl, LiCl, or HCl in that case there. So let's quickly finish this off. Plus, we either have HCl, lithium chloride, sodium chloride, or potassium chloride. Again, either or, not all of them. So that is us now in structural formula, right? Making sure we've got everything in this case over here. Hope that makes sense to everyone in this case. And because we've got everything done the way we did, it is automatically going to be balanced how we've drawn it because we've moved everything one for one. Okay. Hope that makes sense. I'm going to pause for questions. If there's no questions, I'm going to move on to the last bits of this. Yeah, seems to be good. Everyone's on board. Just to make sure you guys are still with me, please give me a thumbs up emoji, any kind of emoji to show me that you're still awake, you're still with me, you're still winning with chemical, with organic chem. Okay, tons of reactions. I'm loving it. Okay, fantastic, guys. TikTok gang, I want to see if you guys are still awake. Are you still following me? Please give me reactions in the chat. Give me a thumbs up. Give me a dancing emoji. Give me something, right? If you're lazy to give me an emoji, then your penalty is you have to click that follow button right now. So click the follow button right now or tap that like button 10 times as a punishment. All right. Yeah, tons and tons of reactions. Loving it, guys. Thank you so much. Cool. Let's jump through. 4.1.6. Give the IUPAC name of alcohol P, right? So let's quickly go back. So alcohol P is what we just did now with reaction 3, right? So reaction 3, alcohol P is this here. So I'll leave that open there. So what is this alcohol that we're dealing with? Okay, some quick fingers there from Rotavile and LT. You guys are awesome there. Um, Novuya's asking, do you write them all? How do you know which one to choose? Novuyo, pick anyone. So I'm assuming you're talking about the NaOH, KOH, lithium hydroxide, whatever. Pick anyone, but just make sure that the last one matches your first one. So if you chose sodium hydroxide, your final one should be sodium chloride. If you chose potassium hydroxide, your final one should be potassium chloride. If you chose lithium hydroxide, your final one should be lithium chloride. If you chose H2O, your final one will be HCl. Just make sure it matches what you started off with. All right, hope that makes sense, Novuyo. Okay, lots of great answers coming in there. People answering question 4.1.6, that alcohol there, and that answer for that alcohol is going to be 2-methyl propan 2-ol, right? So we can quickly put that there. 2-methyl propan 2-ol. All. Or if you want, you can write 2-methyl, 2-propanol. That's also acceptable, right? Either one of those two answers will be acceptable. That's the IUPAC name. Okay, then we're told here reaction 4 is an elimination reaction. Write down the type of elimination reaction. Let's quickly go back up and see. So reaction 4, we go from an alcohol to compound Q, right? Remember, compound Q was an alkene with a double bond. So alcohol to alkene, we're removing OH and another H, which is H2O. Lots of quick fingers are coming in already there. So we're removing H2O. That is going to be called dehydration, right? When you remove water, you call that dehydration. All right, fantastic. Let's keep going. Type of elimination reaction, that's going to be dehydration. Okay, that's 4.1.7. Just to make sure that you guys do understand how that works. So we're sitting with an alcohol. Alcohols have OH. And then we go to an alkene, no OH, right? So when you remove the OH, and you can't remove the OH by itself, because what you have to do is you're going to end up moving, let me go back to the thing here. You're going to end up removing an OH and an H. So you'll take this and take this and end up with a double bond there, right? So when you do that, you're going to take away H2O. That's dehydration. Hope that makes sense to you guys. Cool. Let's go on to 4.2 as we wrap up today's session, and then we leave some time for some questions. So 4.2 says butane 1-ol reacts with propanoic acid in the presence of a catalyst. Write down the type of reaction that takes place. Nice, easy one to finish us off there. Some quick fingers already there. Um, so we've got butane 1-ol reacting with propanoic acid. Hint there, you have a carboxylic acid reacting with an alcohol. What kind of reaction is that? Okay, I'll give you guys 10 more seconds. It's a nice and easy one there. Carboxylic acid is reacting with alcohols. What kind of reaction is that? Let's quickly see how that's going to work. 5, 4, 3, 2, 1. Thanks, Elizabeth, there on TikTok. And thanks to all the answers there on Zoom. 100% it's esterification, right? I'll give you bonus points if you said condensation reaction. So in this case here, we're looking at esterification. And then I'll give you bonus points if you said it's a condensation reaction. Awesome. And then finally, 4.2.2, give us the IUPAC name of the organic product that's formed. So if you were in class yesterday, you would have seen exactly how we name it. So we've got butane 1-ol and propanoic acid. What is the name of the ester that is formed? There's some quick fingers already in the chat there. I'll give you guys 30 seconds to quickly get this one together. What do we get when we react butane 1-ol with propanoic acid? Okay, I see people are already reacting in on Zoom there, meaning they know they got it right. You guys are superstars. Well done, man. Well done, well done, well done. 100%. So butyl propanoate, right? So remember, an ester is going to have two parts. The one part ends in YL, right? The other part ends in anoate. How do we know which one? The alcohol ends in YL. The carboxylic acids ends in anoate. So the alcohol was butanol. So we're going to end up with butyl or butyl, right? And then the carboxylic acid was propanoic acid. We're going to end up with propanoate. And that brings us to the very end of organic chemistry, guys. Well done to all of you who took part. Quick one, I want to get a temperature gauge. How is everyone feeling about this topic so far? I'm still gonna leave space for questions, right? But just to get a sense of how are you feeling about the topic now? Quickly post in the chat. Where's everyone at? Super easy, great, confident. 8 out of 10. Leletu, we're going to get you to a 10 out of 10. Make sure you finish off winter school with us. And then we're probably going to have another round of these classes just before prelims as well. So make sure we're going to, in that session, we're going to push you from 8 out of 10 to a 10 out of 10. Very confident, feeling a lot better. Good, really appreciated. Feel ready for a test now? Fantastic. Paul's feeling confident. Andy's feeling more understandable. Okay, fantastic, guys. Karabo's, yeah, 6 out of 10. Don't worry, Karabo. As long as you're feeling better than before. So, Karabo, if you're 6 out of 10 now, but you came in at a 4 out of 10 or a 5 out of 10, it's improvement, right? We're aiming for progress, not perfection, guys. So, as long as you're just improving and getting better and better, that's the most important thing. Fezaga's at a 4 out of 10. Fezaga, was it a one, two, or a three before? If it was less than four and now it's a four, that's fine. That's still okay, right? You're not going to nail this thing after one lesson. What you need to do now is go back and practice. Go do more past papers, come back, watch the lesson again, and then do some more past papers. How you nail maths and physical science, guys, is through practice. There's no quick fix, but you've got time. This is the winter holidays. So you keep working through the holidays. Term three comes, you're going to keep working, keep working. Prelims are going to be tough. I'm going to prepare you guys right now, right? Prelims are going to be tough. You're going to feel like you got knocked back, but it's okay. It's going to knock that sense into you that helps you prepare you mentally for finals. When you get to finals, trust me, you're going to be feeling very good about yourselves. So just stick around, follow our pages, check out all our stuff we're posting on YouTube, and we'll really help you guys to prepare as best as possible.